In this video we're going to be looking at the CPU, which stands for Central Processing Unit. This is often referred to as the brain of the computer because it does all of the processing. In terms of processing, what it's actually doing is it's going to be searching, it's going to be sorting, it's going to be calculating, and it's also going to be doing all of the decision making. There are two main CPU architectures that you need to be aware of. The first one is von Neumann. This has both the program memory and the data memory all stored in the same place, and it's accessed via one bus. The Harvard method, on the other hand, uses two buses because the program data and the program memory and the data memory are both stored in separate places. So if we're summarising the differences between them, the von Neumann is sometimes slightly slower because it just has the one bus, whereas the Harvard method has two buses because the data memory and the program memory are in different places. However, the von Neumann is therefore slightly easier to implement, whereas the Harvard method is not so much because there are two different places to get the memory from. Okay, you also need to be aware of the components that make up a CPU. So it's made up of 5 things. The first one is the ALU, which stands for Arithmetic and Logic Unit. There's also the controller, there are the registers, and there is also the internal memory, which is sometimes called first level cache. So the controller, this sends and receives signals from all the different parts of the computer, and it makes sure that everything takes place at the right time and in the correct order. And what happens is they travel along a control bus, and it fetches information from the RAM and then passes it back to the CPU. So the ALU, or Arithmetic and Logic Unit, this is the part of the CPU that deals with all the mathematical operations. It also stores the information that it's currently working on and processing within the register. The internal memory, as I've already mentioned, is also called first level cache. It's extremely fast memory where, again, things that are currently being processed can be stored. So in order for the CPU to be able to transmit data between its different components, it needs to make use of buses. So there are 3 buses that you need to be aware of. The first one is the address bus. There is then a data bus, and then finally, as we've already mentioned, there is a control bus. So in terms of registers, there are 3, again, registers that you need to be aware of. The first one is the program counter. There is then the memory address register, and finally the current instruction register, and those are just summarised by their acronyms. So you can kind of think of these registers as being future, present and past. So the program counter is a counter that keeps track of the memory address of which instruction is to be executed next, which is why I've summarised it as future. You've then got the memory address register, which is the address in the main memory that is currently being read or written to. And finally then, the current instruction register is a temporary holding area for the instruction that has just been fetched from memory. So within the CPU, what's happening is what we call the fetch, decode, execute cycle. So for example, the controller might issue a read command to memory to move instruction to add 2 numbers to the register. And then in the decode stage, the controller decodes the instructions to add the 2 numbers together, and it informs the ALU to perform the calculation. It's then executed by the ALU, and it performs the addition of the 2 numbers, and it then stores the result of that in the register. So not all CPUs are equal, and there are 4 things that you need to have in your minds when discussing what would make one CPU perform better than another. So the first one is the size of cache. Now, as we already know, cache is an extremely fast but quite expensive memory. So if you had little cache, if you only had a small amount of cache, then more of the data that's being processed is going to need to be stored in RAM, which is still fast in terms of memory. However, it's nowhere near as fast as cache. So therefore, if you had a bigger cache, then you would need to rely on storing things in RAM a lot less. So another factor is the clock speed, and it's measured in Hertz. So if you have a fast clock speed, then it's going to be able to carry out the fetch, decode, execute cycle a lot quicker than if you have a slower clock speed, which is highlighted quite nicely in this diagram. Okay, so we've just mentioned the word Hertz, That's not what happens when someone punches you. It actually refers to one tick of the clock. So when you're buying a computer, you're probably going to be looking at thousands of ticks of that clock per second, because you'll be looking at a computer that works in gigahertz. So the third factor then that affects the performance of a CPU is the number of cores. So you'll have often heard of dual core or quad core. What that actually means is, if you have a single core computer, so it just has one core, then the instructions can only happen one at a time. Whereas if you have a dual core processor, then 2 instructions can be carried out at the same time, and a quad core, obviously 4 can. So a dual core, essentially, in theory, should be twice as fast. Now, it doesn't always work like that because there are still some bottlenecks, but generally it is obviously a lot quicker the more cores that you have. And finally, the type of processor that you have also affects its performance. So there are 2 types. There is RISC and CISC. So RISC stands for Reduced Instruction Set Computer, and CISC stands for Complex Instruction Set Computer. So with a reduced instruction set, it means that for the programmers it is harder to code software for it that will run on that CPU. However, it does run faster because there's less cycles that needed within the CPU to do the same task. Whereas a complex instruction set computer is easier for the programmers because they don't have to write quite as many lines of code in order to get the processor to do the same thing. However, this can, of course, slow it down. So the RISC tends to be a little bit faster, as I said, because it needs to do less cycles.